Hello, and welcome back to a new episode of Plan C, Ocean Interventions to Address Climate Change. As always, I'm your host, Anna Madlener, MRV Manager at the Carbon to Sea Initiative, and I'm joined by my co-host, Will Burns, who is the Co-Executive Director of the Institute for Responsible Carbon Removal and Associate Director of the Environmental Policy and Culture Program at Northwestern University. Hi, Will.
Hi, Anna. What's in store today?
Yeah, today we're talking with Grace Andrews, who is the founder and executive director of Hourglass Climate and former head of science at Vesta, a company focused on coastal carbon capture using olivine-based beach nourishment. This year, Grace launched Hourglass, a research nonprofit dedicated to developing the tools and the science for rigorous quantification and environmental monitoring of mineral-based ocean alkalinity enhancement. She's been a very prominent voice in this field since its inception, and I've loved her engaging talks about Vesta's permitting process in the Hamptons, where community involvement really was key, and both honest community engagement as well as thorough, transparent assessment of OAE's, or Ocean Alkalinity Enhancement's, ecological impacts have recently really slowed down some permitting processes for important field trials, and therefore, rightly so, have also become crucial decision factors for buyers and funders. So today, we'll focus on the environmental monitoring and precise carbon removal quantification that Hourglass is providing as the measurement, reporting, and verification, or short MRV, lead for one of the largest coastal OAE trials to date. Will, what excites you most about this episode?
Well, I've been following Grace's work pretty closely, and I'm eager to hear about this new nonprofit's research model and whether, more broadly, this kind of research model of third-party oversight in the nonprofit sector can really help in terms of ensuring the integrity of mCDR. And I think it has some real potential to drive change. And as a bonus, Grace is a Northwestern alum, so go Cats.
Nice. All right. Yeah, I would second all of what you said, and I'm eager to talk with her and hear from her. So let's bring in Grace. Good morning, Grace. How are you?
Good morning. I'm doing really well, and I'm really excited to be here and to talk with you guys. So thanks for having me.
Awesome. Yeah, thanks for coming on. Let's jump in. Tell us a bit about your journey, who you are, and how you got into the marine CDR world.
Yeah, absolutely. Well, I like to put it simply in terms of who I am in this space and what I'm trying to do here. I have spent my entire career trying to understand how to dissolve rocks to regulate global climate. It's really not more complicated than that. And I find this riveting. While other people may struggle to see the beauty, but this stuff is really cool. But I'd say my pathway into marine CDR is maybe a little bit unconventional in that it started on land. I spent the first easily half, maybe more of my career working on land. My earliest research as an academic, not too many people know this, but started studying chemical weathering and alkalinity production under glaciers and ice sheets. I got really interested in how the physical movement of glaciers over bedrock can grind that rock into tiny particles called rock flour, and in turn substantially increase the carbon removal potential of glaciated landscapes. I was interested in this in terms of the role glaciers and ice sheets can have on geologic timescale climate, but it turns out this happens to be a really awesome natural analog for enhanced rock weathering and that process of grinding up rocks and minerals to capture carbon. So moving into the CDR space broadly and enhanced rock weathering was a really natural progression for my work. But I started there on land as well. I spent a bunch of years at the Leverhulme Center for Climate Change Mitigation in the UK, working on enhanced rock weathering, adding these kinds of rocks and minerals to agricultural soils. But I pretty soon got obsessed with this idea of how can we use the ocean for enhanced rock weathering. Honestly, mostly just because of the scale potential. You guys may know this. The ocean is really big. It's really, really big.
I've heard rumors.
Yeah. And so it just felt like if we're serious about gigaton scale CDR, the ocean is going to be the place to make this happen. So from there, I left academia, I jumped into the startup world. And, as you said, I was the chief scientist at Vesta for a number of years, pushing forward the R&D on ocean-based enhanced rock weathering. And now I'm continuing my journey at Hourglass, working on a broader range of marine CDR strategies.
Okay, awesome. Say a little bit more about ocean-based enhanced rock weathering. That is one way of framing it, of course. As far as I know, what Vesta did was olivine beach nourishment. Help us understand, how that fits into the broader mCDR, marine carbon dioxide removal pathway scheme.
Yeah, absolutely. So Vesta was focused on adding a particular kind of alkaline mineral called olivine into coastal protection projects broadly. So beach nourishment, but also building what are called nearshore berms, which are wave attenuation structures with these kinds of minerals, but really looking to integrate enhanced rock weathering into coastal protection strategies to offer a really important co-benefit to society, protecting coastlines. So I love that model, looking to actually merge climate adaptation with climate mitigation. In general, though, you can think about adding alkaline minerals to the ocean really across the whole continental shelf. There's no need to limit it to the sorts of coastlines that Vesta was interested in. But the idea here really is that when you add these alkaline rocks and minerals to the ocean, they interact with carbon dioxide in that seawater, they gradually dissolve, they produce alkalinity, and they end up through air-sea equilibration, drawing CO2 out of the atmosphere. And so you can do it with olivine, but you can also do it with a range of other minerals too. There are other companies out there, like Planetary Technologies, that have used the mineral brucite to basically run the same process.
So let's get into Hourglass and talk a bit about what it's intending to do and your role in it. So as you mentioned, you spent several years with Vesta, and then why did you choose to spin out this research nonprofit from the company, and how should our listeners think about this model?
Yeah, I had a great time as head of science at Vesta. I loved every minute of being there, and it was eye-opening in terms of learning about how the real world works outside of my academic bubble that I'd previously been living in. But I decided to leave Vesta and start Hourglass. The reasons were manifold, like all big decisions. But at the heart of it was through my time there, I really acquired like a deepened realization that the ocean is a really complex place to work in terms of the fact that it's a commons, right? It is a shared resource. It supports the lives and the livelihoods of people around the globe. It's a vastly understudied ecosystem. And so, although, as I said, it has tremendous potential to help society combat the climate crisis, if we have any hope of getting widespread consensus to allow scaled marine carbon dioxide removal, then stakeholders around the world are going to need transparent access to the foundational data sets that underpin marine technologies, particularly as they pertain to their sort of fundamental safety and efficacy. And they're going to need to trust those data sets, right? And not have questions or concerns about for-profit motives that might be influencing those data sets. So we did amazing work at Vesta, and I stand by it. But some of the feedback I got while I was there were comments from people saying, Grace, we know you, we trust you, we believe in the integrity of the work you're doing, but the global stakeholders don't know you, right? And they need to be able to trust you too, and trust the work that you're producing. So I ended up concluding that for the maximum impact for this work to have, it needed to be in a new type of vehicle. And so that's where I really landed on a nonprofit research organization as a better fit for driving this work to have the biggest impact.
Do you think there might be any concern that, given the fact you were with a for-profit organization, that you're now scrutinizing its work, that you might not be able to be as objective as you could have if you had never had a relationship with the organization, or at least people will have that perception?
I hope not, right? I've started this initiative because I fundamentally believe that this work needs to be done without a for-profit motive. And there may be like skepticism that we're not truly independent. Honestly, even like 3 seconds ago, Will, you framed this as, Grace, you spun out this entity. I didn't spin out Hourglass. I left Vesta and formed a new entity that is truly separate and autonomous. We have no structural relationship to Vesta. Our work together is really limited to a services contract to independently monitor and publish the results from their field trial. And I think an important feature in understanding why we can be objective here is to understand that, we are monitoring this field trial, but we are a research institute. We are not an MRV company. So our business model does not rely on a long-term relationship with Vesta. In fact, sort of the big idea here is that we participate when and where there are critical research questions, and when the answers to those questions are important for the public to have access to, as I said. But when those questions are answered, we move on. And so, this is something where we're funded through philanthropic grants. And that is our motivation and our driver to do independent research. And it's not, again, to have sort of a commercial relationship with Vesta in the long term. I want to emphasize that conducting this research independently is the core tenet of our model, right? So when we publish the results from Vesta's field trial, transparently and contractually, we are not obligated to incorporate edits from them, right? We have the freedom to report our findings as we see them. And so I think, that's what we're bringing to the table.
And does that mean that your funding will always flow from independent third parties, or does some of it derive from the projects that you're asked to review?
We have a mix of funding sources. What I can say with the Vesta work is our funding is independent. We are very much vastly funded by philanthropic grants. Any funding that we receive through services contract, it's like single digits of our overall funding. So we are really reliant on philanthropy to get this work done. And again, that very much helps us bring independence to the table.
Do you contemplate that that's the business model in the long term, or do you see more of a service contract model moving forward?
Yeah, I think it'll always be a mix of philanthropy. Government grants are obviously a big thing that we're looking to bring in, and then there'll be some services income. I think, like on any good organization, we're looking to diversify our sources of funding. But I don't ever anticipate that services are going to be the majority here by any means.
So during a recent webinar at Ocean Visions, you referenced the potential parallels between biomedical research and mCDR. Could you expand a bit more on that?
Yeah, so, as I previously said, I kind of came to the conclusion that I didn't think a for-profit vehicle was the right vehicle to do this kind of foundational R&D. But it's also, I think it's really important for folks to understand what actually goes into marine CDR field trials in terms of the time and resource it takes to get this work done. So to put it simply, right, any marine CDR field trial takes easily $10 million and years of work, right? When you think about running a project, you've got at least a year of stakeholder engagement before you're submitting your permit. You're doing a year of modeling before you submit a permit. Permitting itself takes at least a year, probably. Then you do baseline work. Then you deploy the project. Then you monitor it for 3 years. Then you spend a year writing up papers. I mean, these are huge, huge endeavors. And they are complex. They are multifaceted. They are interdisciplinary. The sheer scale here is really enormous. And so I basically looked at this and said, okay, the for-profit vehicle isn't, I think, right here. But returning to academia is also not right here. I mean, I don't know an early career academic who has the capacity to hire 3 postdocs to live full-time at a field site for 5 years, right? Like, that's just not how academia works. And so I started to look at other models, right? And I really did a deep dive into the Nonprofit Research Institute model, because it makes up a meaningful part of, other fields like biomedical. And so in my deep dive, I kind of tried to understand, in the biomedical context in particular, what's the unique role that the Nonprofit Research Institute is playing there, and could that be a fit for marine CDR too? In the end, my sort of theory here is that in the biomedical field, these nonprofit research institutes, they are tackling problems that have 5 features. So 1, they have strict focus. 2, they feature large-scale collaboration. 3, they feature high-risk innovation. 4, translation from basic research to real-world application. And 5, the production of public goods. So I founded Hourglass to basically try and fill a similar role in CDR, to tackle ambitious, interdisciplinary, translational, high-risk projects and produce public goods. And I think it's kind of a natural fit, but I'm particularly driving Hourglass to really zero in on things that I think a nonprofit can do that you don't really have capacity for in these other avenues, such as, for example, large-scale monitoring of novel trials.
Okay, so you mentioned your focus on answering key research questions. Can you say what these questions are at the moment, and what projects are you currently working on?
Yeah, I mean, so we are tackling a few different sort of big initiatives. I kind of put them into 2 buckets. So again, a focus on field trials and a focus on developing tools as public goods to actually help quantify the safety and efficacy of field trials and projects, mCDR projects in general. So in terms of the field trials component of what we're doing, we are working with Vesta to monitor and independently analyze their field trial in North Carolina. That's a big part of what we're doing, as I said. We're also working with Woods Hole, the USGS, and the National Park Service on a field trial in Massachusetts that's placing olivine and carbonate minerals in a marsh. And so that's one of the projects that's been funded through the NOAA program. So we're focused there, and we're also, I sort of hesitate to say this out loud because it's such a big thing that I'm staring at on the horizon, but we are also scoping our own independent field trial for, in theory, maybe 2027. So we're sort of working with partners, and we're doing our own. So that's kind of
spicy information.
I know. I just met with the EPA about it, so things are kicking off.
We have to reorganize our entire questions now, Grace.
There's not too much to say on it. Like I said, we'll see. And that is very much fundraising dependent, so we'll see how it goes. But so that's the sort of our field trial portfolio. And then, in terms of tools, like I said, we're focused on building quantitative tools to help predict and assess carbon removal from projects, as well as the environmental impacts of projects.
So if I understand your model, then let's say you're asked to do this assessment from a project like the HUI project, right? At the end of the day, you independently release your results, right? HUI has no right to stop you from doing that, right? Once they've called you on to be part of the assessment.
Well, with regards to the project that we're doing with Woods Hole, there we are named collaborator on as I said, on a NOAA funded project. So we will be publishing all of the results for peer review as a team.
But this would be the same with Vesta, right? If at the end of what you had done, you have an independent right to publish whatever you find, correct?
Absolutely. Yeah, absolutely. And again, we see the publication of those data sets from these field trials, such as Vesta's, as the production of a public good, right? That again, everybody should have access to the first information about the real world efficacy and safety of ocean-based enhanced rock weathering. Everyone deserves access to that so that we can start making communal decisions about whether or not we want to see these types of projects moving forward.
Is there any proprietary sort of data that Vesta won't provide you with access to? Because when I hear transparency, I think that's really important and showing everybody the results. But I think people can be a bit misled sometimes that they're seeing the whole thing because of proprietary considerations. Do you think that's a serious concern with these kind of projects?
Well, what I can say is that we are the ones generating all of the data from the field trial. So Vesta is not in any way involved in the monitoring of that field trial. So they don't really have the ability to withhold data from us because we're the ones producing it all. I think the part of the carbon removal equation that we are not tackling in Vesta's project is the emissions side of things. So we are monitoring the field trial. Of course, the net carbon removal from any project is, removal minus emissions. We're tackling that removal piece, where, what they end up concluding in terms of emissions and their LCA, that is outside of our scope.
All right, so let's dig a little deeper there, pun intended. During that same Ocean Visions webinar that we briefly mentioned, you shared some preliminary results from those trials that you monitor for Vesta. In terms of your key conclusions, you shared some really interesting information that I know people were very excited and curious about. Could you go over those and tell the audience why they're so exciting and interesting?
Sure. So we're just getting the first carbon removal data sets in from Vesta's field trial in North Carolina. What I showed in that webinar was some of the pore water profiles from the site. So what that means is for a mineral-based strategy, again, it's the minerals dissolving on the seafloor where you get the, in theory, alkalinity production. And so we have been going out and collecting water from between those sediment grains, that's pore water, and measuring the carbonate system on them. And we're doing this in a profile, so you can look at it from the water column all the way down into the sediment to, say, 20 centimeters. And, what you expect to see when you envision olivine dissolving in this carbon removal mechanism is you expect to see PCO2 going down, basically that CO2 getting gobbled up and converted into, in theory, alkalinity. You expect to see pH going up. Again, that, consumption of CO2 and, in theory, that production of alkalinity makes pH go up. And you expect to see alkalinity go up, right? So those are some of the key key things you're looking for to understand, like, is this working? So we went out and we collected these pore water profiles from both the olivine site, but also control sites as well, to understand sort of the natural background against which to compare the olivine treatment. And what we found was pH went up, great, check. PCO2 went way down, great, check. But what we found additionally was that alkalinity actually also went down, right? So this is a Ocean Alkalinity Enhancement strategy where alkalinity went down. A little bit of a misnomer. And so why this is interesting, of course, is it kind of, bucks the model about what we all expect to happen. At the same time, we have been running geochemical simulations of the site, and it's actually exactly what we thought would happen, which is really cool. One of the tools that I have alluded to is what's called a reaction transport model, which is something that can predict the geochemistry of these projects. We ran that reaction transport model. This is what it said would happen. Frankly, we were skeptical of our model outputs because we were like, really? And then we went and got the field data, and it was more or less a perfect fit. So what we think is happening in that scenario, in this field trial, is that we're basically jacking the pH way up, we're jacking the alkalinity way up, but we're jacking it so far up that we're then flipping into carbonate precipitation. So we are super saturating the pore waters with respect to the carbonate mineral, and it's precipitating out, which then consumes that alkalinity back up.
And would you say that this is the conclusion of this is that less alkalinity, i.e. olivine, should be added, or is this just sort of tweaking our understanding of what olivine beach nourishment means? Because just precipitation is not necessarily bad. It's still carbon removal, right? It's just less, I guess, than if it were all transformed into dissolved inorganic carbon. Is that correct?
Yeah.
So what does this mean for, the future of olivine OAE?
Yeah, so I think what you just said is important to realize, which is indeed that carbonate precipitation is still CDR, right? So it's just on a mole per mole basis about, again, in theory, about half as efficient as if you were producing alkalinity. It's actually not quite that bad because when you produce alkalinity, there are losses in efficiency further down the chain. So it's not actually that bad. I don't know. If I could ballpark it, maybe 30%, I don't know. But so it is still CDR, and it is, our own calculations of emissions versus the removal potential here. You are definitely still like very much in the net removal category. So this is not like a nail in the coffin at all. It's, as I think about it, something to think about in terms of like, is it enough carbon removal to make this, a viable strategy in terms of the cost per ton of carbon removal and other things?
And I would assume that spinning this a bit further, if it precipitates immediately, or put differently, as you just alluded to, alkalinity production has efficiency losses further down the line, which I guess, is more of the general challenge around mCDR, around air-sea gas exchange, etc. So does this in turn mean that actually MRV becomes easier because really the CDR is taking place immediately on the spot, and we don't have to worry about long-term equilibration or other efficiency losses down the line? But does it also in turn mean there's a bigger focus on the ecological impact because you're producing precipitation that you weren't accounting for?
There were a lot of things embedded in that question.
Okay. MRV was the first one.
I think in terms of MRV, what this might mean is that MRV could be easier simply because it is, I would posit, substantially easier to track a solid mineral that settles on the seafloor than a molecule drifting around the ocean, right? It is pretty easy to go get a sediment core and to measure its carbonate content. it is substantially harder to generate a mole of alkalinity and then watch it, ultimately potentially end up in the deep sea, right? So I think it could be easier MRV in that regard. And I also think it's kind of interesting from an MRV perspective, because I think it might actually just help with stakeholder engagement, in that it's a lot easier to conceptualize RIN removal when you're saying, I'm going to form a carbonate mineral on the seafloor, and I'm going to grab it off the seafloor and I can show it to you, right? I think one of the things I've heard a lot as I've worked on ocean alkalinity enhancement is people are kind of like, what is alkalinity? Right? What is that word? What does this mean? And it's something you can't see it. You can't hold it. And so I think that's been a real struggle, it really means you have to trust chemistry, and chemical measurements, because you can't see it. You can't. So forming carbonate minerals, it kind of gets away from some of those issues, which I think could be important. But I do want to layer on here. I think this observation that we formed carbonate minerals, time will tell, but I'm not convinced that this is going to be the big picture conclusion for this strategy. I say that because, we're seeing this now when we have a really high concentration of olivine making up our sediment column. But sediment transport is a powerful thing. Hurricanes moving along the coast of North Carolina are powerful forces. And we very much expect and are already seeing that olivine disperse and dilute into natural sediment, native sediment at the site. And so when you start diluting that olivine, again, you're diluting your signal, which means you're not getting the same massive pH swing. You're not going to get that same supersaturation. So if I had to guess, I think this is probably on the spectrum of the timescale of this strategy, a short-term effect. And that later on, again, as we get the dilution, we'll probably move back into the regime of alkalinity production.
What would you define as long term? What kind of timeline is going to be important for assessing kind of the ultimate effects of this sort of intervention?
Yeah, well, I think when I think about the timescale of these projects, it's basically the timescale of how long does it take for this olivine to dissolve, right? That itself is a function of primarily the grain size, the actual size of the particles that you've put into the ocean. The smaller the particle, the more quickly it dissolves. So, it'll range depending on the project. But in general, we think of this as a multi-decadal timescale. So 10 years, 30 years, potentially 100 years, right? So that's the total timescale of the project. But I think the timescale of assessing its efficacy is shorter, right? I think we can do it basically now, because again, that sand that Vesta placed in June, it's already moving around. So we already have the capacity to look at the olivine when it's in this big pile of pure olivine, but we also already have the capacity to look at areas where it started to mix into the native sediment and look at the different geochemical responses under those two regimes.
Okay, so that's interesting because you're saying, like generally speaking on the, I guess, like climate relevant timescales, these are projects that are going to sort of extend over decades. But in terms of actually quantifying the removal of one particular project, whether that's a commercial field trial or not, that is actually possible based on the measurements and observations you're doing to a certain degree of confidence, I suppose.
Yeah, I think about the strategy here in terms of quantifying carbon removal from these projects as twofold. You need the in situ empirical measurements, which, that's what we're out there getting right now. It's honestly just I think a really big accomplishment to say, like, we can measure the carbonate system changes from this intervention, right? This is part of the narrative that I think marine CDR, ocean alkalinity enhancement, gets, criticized for a lot, is the signal to noise ratio is is terrible. You'll never measure anything in the field. It's going to be all model based. How can we trust models? Like, et cetera, et cetera. The biggest result to date is that we can measure this. Like, I'm measuring pH swings in the ocean today, measuring CO2, PCO2 going down, and I am measuring either, carbonate precipitation and potentially later alkalinity generation. These are resolvable signals. What that means is, again, eventually, I do think that this olivine on the decadal time scale will disperse to the point where that signal to noise ratio really is a challenge. But that is where models like our reaction transport model can play a role. So we can build a model that predicts carbonate precipitation, as it already has. We can build a model that predicts alkalinity production. We can use years of real field data to validate that model and give us the confidence that we can use that model to predict the carbon removal on longer timescales past the point where we are getting resolvable signals in the field.
That is a really important point. And we've tackled the quantification bit of the challenge. The second part of my long and complicated question was around how that changes your theory, your research question around ecological impacts. It's another really critical piece for OAE broadly. As we mentioned in the introduction, the uncertainty around ecological impacts is a big challenge right now. It's sort of slowing down permitting of really, really relevant field trials. I'm making another complicated question, sorry. Did that early result from the trial, change anything around your understanding of ecological impacts? And also then bigger picture, how are you thinking about, working towards frameworks of environmental impact?
Yeah. Well, I think, at a high level, this early result around carbonate precipitation, it doesn't scare me very much for two reasons. One, there is already a whole lot of carbonate in the ocean, right? It makes up a percentage of every beach probably in the world. So this is not something that I think is inherently going to be an issue for marine life, the formation of some amount of carbonate. So that's one piece. And then, of course, also as I said, I think this will probably be a transient effect. And so, again, in terms of the big picture environmental impacts of a project, a transient effect doesn't worry me too much at this moment. When I think about the potential environmental impacts from these kinds of strategies, the placement of minerals, the biggest one that I think people are thinking about is not really around the carbonate system, but really around the release of other elements from the dissolution of these minerals. So these minerals are, they've got trace elements in them, and they have some trace metals in them as well. When you dissolve these minerals, you are also adding some amount of trace metal to the ocean. That, for me, still remains the biggest thing that I think we should be taking a hard look at. We are, of course, really focused on that in a few different ways at Hourglass. It makes up a huge part of our monitoring portfolio for the Vesta field trial, for example. We are doing surveys of both the benthic macrofauna. So those are the critters that live in the actual sediment. So think worms and snails, critters that are like living in the olivine, right? We're also doing surveys of mobile fauna. So think fish, for example, things that eat the things that live in the olivine. So we're trying to really look at the impact on both their community structure. So that would be their the impact on diversity, abundance, as well as we're actually collecting samples and measuring it for the potential accumulation, I should say, of trace metals. which will tell us again about those living in the olivine, but also further, up the food chain. So we're taking, as I said, a hard look at this. We're trying to do this like at the A++ level. We're doing it. We're doing quarterly surveys to look at how this might change seasonally as well as interannually. So we'll be doing this program we're scheduled right now for 3 years to be doing this work to really make sure we understand both short-term and long-term potential impacts.
Is that how you would define long-term impacts? If we get to the 3-year mark, we'll see most of what the potential impacts would be in terms of trace metal releases on organisms?
Yeah. I think so. And a few reasons for that. When you think about the life cycle of these organisms, it's, it depends on the organism, but, we're talking days, months. And so looking at something for 3 years actually gives you multiple generations potentially of these organisms' life cycle. So that's one piece. The other piece is, of course, I think the exposure to these organisms also goes down through time, right? It goes down through time, again, because as the sediment is transported through time, your concentration in any square meter goes down. That's sort of inherent to how these projects operate. So your exposure goes down through time, and you also you get the most amount of dissolution at the beginning, because that's when you have the really fine-grained material that just basically dissolves immediately. So the highest dissolution rates are at the beginning. The highest concentration of this material is at the beginning. The exposure goes down through time. We're capturing multiple life cycles. I do feel confident that 3 years will be sufficient.
Yeah. So one of the other things that I had read years ago, and this may be moot if you think that you're actually seeing a decline in alkalinity, but I read a couple studies that express some concern about alkalosis for certain species, like littoral crabs, for example. Do you think that's a serious concern when it comes to these kind of projects?
I think it is something, again, that we need to take a look at. But I mean, exactly to sort of what you said at the top of the question, the alkalinity exposure goes down through time. So you do have a meaningful increase in alkalinity. It will be transient. And so again, long-term impacts, you're likely to have any alkalosis actually be, potentially short-term, but not long-term.
Is that also true if the project is sort of continuous and or repetitive, or is it only true if it's a one-time experiment?
Yeah, great question. I think obviously if you're just continuously adding more and more of these minerals and you're keeping the minerals in steady state, then the response will be in steady state.
Mm-hmm.
So to me, that is really the importance of responsible project design, and really, again, understanding both short-term and long-term impacts. Because the short-term impacts, again, if you're just continuously adding material, become long-term impacts.
Mm-hmm.
We need to understand both timescales and have that information to make smart decisions about how to responsibly deploy these technologies. In general, I would argue that nobody should be thinking about deploying any alkaline mineral into the ocean such that we are absolutely coating the seafloor in this stuff, right? I mean, it's to me pretty obvious that dramatically changing seafloor habitats is not what we want to do here. It's about deploying these materials in a manner that is creates a incremental and almost unnoticeable change to marine habitats. And it's not just about alkalinity and trace metals. It's also about the fact that when you're adding these minerals, you're adding a purely inorganic substance to the ocean, right? Diluting the organic matter content of the sediment. that's really important as a food source. You don't want to dilute it too much. You are fundamentally changing. People even think about how mined minerals have different particle shapes than really rounded sand grains from the ocean. So you're changing the shapes of the sediment that the organisms are living in. You're changing the permeability and porosity of the sediments. Like, we want to keep this to a minimum in order to have this not have significant impacts on habitats, again, against these wide range of potential impacts.
So taking that assessment, I want to put you on the spot. There is a big desire for and several projects ongoing already, but a big desire for a, unequivocal environmental risk assessment for field trials that people can point to and that companies can point to and that companies are held accountable to, right? Do you think that Hourglass might be a group that will work towards that and develop it? Or if not, how do you think we will get there?
Yeah. I mean, I certainly think, I know there are initiatives out there to do that. And I think Hourglass is very interested in being a part of that process. We have a unique perspective, I think, in that myself and some of my team have now been involved in the permitting and execution of multiple marine CDR field trials, which I think is actually something not a lot of people can say at this point, which is kind of a problem. That's a side note. But I mean, we have years of experience, honestly, working with communities, regulators, NGOs, academics, trying to understand what questions they have about environmental impacts, what data they want to see. And I think also equally important, we know what questions they should be asking, but perhaps didn't know to ask because, until a project showed up on their doorstep, they'd never heard of marine CDR, right? And so I think all of that lived experience can play a really important role in designing environmental impact monitoring frameworks that are useful to, again, this broad range of stakeholders.
Yeah, that leads logically to my next question. I know that you are not you're not involved directly in the permitting process, but as you indicated, a lot of the research you're doing is pertinent to that process. What role has Hourglass played in terms of providing information that's been incorporated into permitting, if at all, either for Vesta or in the case of the Loch Ness project or any other projects?
Yeah. Well, I mean, to date, to the best of my knowledge, the data that we have generated out of this project in North Carolina, for example, hasn't been involved in any permit applications, primarily because it's so new, right? The project launched in June. The first time Vesta saw the results from this project was at a talk I gave about a month ago, right? They were in the audience and were there to see it along with everybody else. So it's so new. But that said, I do anticipate that the publications that we generate will be really important pieces of evidence for future permitting applications, again, for a wide group of stakeholders. That's part of our goal here, indeed, is to produce something that, people can point to as, real world impacts. Because obviously to date, our best understanding comes from benchtop studies on environmental impacts, which just lack the complexity of the natural world. So, the best thing we can do is provide that real world data.
All right. Yeah, I think we've covered a lot of very in the weeds topics. Arguably, another pun intended.
I can't help it.
You can't help it.
Go ahead, nerd out.
Obviously, Hourglass has a very pivotal role to play in the field right now. especially around, as you mentioned, the unique experience that you guys collected. I can speak from my own experience planning a field trial right now. It's a lot of work and it's a lot of firsts for everyone. I wonder if we could summarize the episode with your top 3 research picks at the moment. What do you think, whether that's you or the rest of the field, the others? What do you think we should be really drilling down on at this point in time?
Yeah. I mean, obviously, the answer I have to give to one of these, right, is we need more field trials deployed in a more diverse group of settings. At this point, one set of data is one data point, 2 points make a line, 3 points make a conclusion. So we need to get to that point across the whole spectrum of potential technologies. So we got to do that.
When you say diverse settings, do you mean other places? Because I actually kind of feel like we need more of the same field trials in other places so that we can draw conclusions from, as you said, like the one data point. Is that data point becomes comparable if a lot of the, other data points have been conducted under similar conditions. But right now, most of the few field trials that are happening are quite heterogeneous, actually.
So you're suggesting that we need repeat field trials, in the same location or in diverse locations? I didn't quite follow that.
I guess diverse locations, if that's what you mean with diverse. That's what I was wondering, if that's what you mean with diverse.
Yeah.
Okay.
Yes, I do mean repeating the same kinds of technologies in a spectrum of locations. Because again, the natural world is complex. We need to understand what I want to understand is the large scale potential. And indeed where some technologies may work better or less well, right? It's also really important. So certainly that. I think we need, you won't be surprised to hear me say this, I think we need better knowledge transfer between, for example, STEM scientists and industry and social scientists on how to do community engagement, right? I think that community engagement and thinking about how we can talk to and connect with folks about these kind of strategies, how scientists can do this and play a really impactful role in it is something that gets said a lot, but people don't spend nearly enough time actually doing and thinking about and implementing on. So I would love to see more work in that arena. And then I think the one other thing I'll mention, because it's something that I also just can't stop talking about at this point, is I want to see us thinking about not just environmental impact frameworks, which we touched on, but again, the building of quantitative tools to assess environmental impacts. And the distinction I'm making there is that an environmental impact framework or environmental impact MRV, EMRV, people like to say, that tells you to date, that tells you what to go do. But we really need to understand, what do we do with all this data, all this environmental data that people are generating, right? Like, it's not just important to go make measurements. You have to be able to take those measurements in and contextualize them and interpret them and make conclusions about whether or not that had positive or negative impacts on the environment, whether or not that particular project was done responsibly, whether or not we should be buying carbon credits from that project, right? We need to be able to do something with all this data in a quantitative sense. So I think that's a piece that's really missing from the discussion. It's something Hourglass is focused on, at least in some subsets. Like, we're working on a ecotox, adapting existing ecotox models to try and tackle at least a piece of this, but it's a much bigger picture than just ecotox. So.
Yeah, that's a really great point. Something that we focus a lot on in terms of the removal quantification, right? But actually something I often think about as well when people use that term EMRV, because to me, EMRV sounds like something you can quantify. But what we're talking about is not about something until just now, right? About something that we quantified, but just doing like an assessment, and it's different for that reason. So thanks for that clarification and nuance there. I think it's really helpful. Awesome. Thank you so much, Grace, for joining us and spilling out all the details. It was really great to go into it. I hope that that people will enjoy it. And thanks as always to our listeners, and follow us wherever you listen to podcasts, share us widely. And with that, we'll say goodbye. Thanks, Grace.
Thanks, guys, so much.
Thank you, Grace.